Welcome, everyone. In this lecture video, we are going to discuss the concepts of pH and pOH as a means of quantifying the relative acidity or basicity of a reaction mixture. And so the learning objectives really boil down to putting forward a definition of what do we mean by pH and pOH, and getting used to calculating pH and pOH using chemical equilibria concepts. So I want to start off by a quick recap. In the previous lecture video, we introduced this concept of the autoionization of water, where we see water essentially reacting with itself, transferring a proton from one water molecule to another to form hydronium ions and hydroxide ions. If you write out this autoionization reaction, you can form the associated equilibrium constant, which we have a special name for. We call it Kw. Which is the product of the concentrations of hydronium and hydroxide. And of course, that's equal to 1.0 times 10 to the minus 14 if we're at 25 degrees Celsius. All right, and so if we look at this relationship in a little bit more detail, we see a couple of important points to note. First, the concentrations of hydronium and hydroxide are inversely proportional to one another. Right? So hydronium and hydroxide impact solution properties and solute behavior. And all of these pieces we really need to keep at the forefront of our minds when we're starting to explore acid-base equilibria. And so what becomes helpful is to come up with a way to classify solutions as either acidic or basic on the basis of these relative concentrations of ions. And so using our Kw expression is going to allow us to really put forward, I think, some natural definitions involving the concentrations of OH minus and H3O plus hydronium. So the Kw, right, the product of both of these ions is this 1 times 10 to the minus 14th, again, at 25 degrees Celsius. And we're going to get lazy and probably not write that out all the time. So we can effectively assume that we are dealing with acid-base solutions at room temperature, unless I say otherwise from this point on. Okay, so on the basis of this autoionization constant, we're going to classify a solution as being neutral if it contains equal concentrations of hydronium and hydroxide ions. In other words, if the hydronium and hydroxide ions are both 1.0 times 10 to the minus 7 molar, we have a neutral solution. If that ratio gets skewed, if, for example, we have a greater concentration of hydronium ions, we're going to call that solution acidic. Okay, so if this number goes up, it becomes acidic. Of course, if hydronium ions go up, hydroxide ion concentration must go down. Conversely, if a solution contains a smaller concentration of hydronium ions, then we are going to classify that solution as being basic. And so we take the product of both of these. In all cases, we'll get that Kw value. But again, it depends on how this ratio is set up. More hydronium, acidic; more hydroxide, you get basic. Equal amounts, you have a neutral solution. Okay, so that all seems fine and good. However, when we're dealing with these concentration units, we probably saw when we're dealing with these numbers on the order of 10 to the minus 7 or 10 to the minus 14, these are very small numbers. And we find that during the course of a given chemical reaction or for different chemical species, the concentrations of OH minus and H3O plus are actually going to span many, many orders of magnitude. And so it becomes convenient to introduce a logarithmic scale to more easily talk about these different concentrations. So the first one we want to put out there is this so-called pH. The definition of pH is essentially say, take the negative log of the hydronium ion concentration. So when you see this little p, you can think of the p as an operator that says, take the minus log of whatever follows me. So if you write out p followed by an h, we're going to say, take the minus log of the H plus concentration, right? And of course, remembering H plus concentration and hydronium ion concentration are synonymous. Similarly, pOH is defined as the negative log of the hydroxide ion concentration, right? And in all cases, we're writing out log. Once again, you oftentimes see us be a little lazy with this. What we're talking about when we're talking about pHs, we're talking about a base 10 logarithm. All right, now, there's some important relationships that come about when we're looking at pH and pOH. So first of all, I want you to have this little relationship in mind up here, and we can either write it in terms of hydronium or H plus. Of course, hydronium we need to put here, and then we change this to H3O plus. Same end result, we end up with this Kw expression. And essentially what I want to do is say, okay, let's start with our Kw expression and just introduce these, minus log terms on both sides. So essentially take minus log of both the left and right-hand side. If you do that, you end up with this first equality. And remembering from our property of logarithms, if you have the logarithm of a product, you can separate that and say that's going to be the log of the first term in that product plus the log of the second term in that product. So a minus log of H3O plus times hydroxide gives us a minus log hydronium plus minus log of hydroxide. And so you put both of these together, we're going to end up with our definitions then of pH and the definition of pOH. And so at 25 degrees Celsius, right, Kw is going to be here at 1 times 10 to the minus 14. And so basically, at 25 degrees Celsius, we have this relationship that says the minus log base 10 of 10 to the minus 14, which is simply 14, is equal to the pH plus pOH. Right? So anytime you're at 25 degrees Celsius, this relationship will hold. Okay, and so we want to connect these definitions then with our vocabulary. So as you know, in pure water, every time you have an H plus forming, you're also getting an OH minus, right? So according to equation 3, we're dealing with this Kw expression. We know that at 25 degrees Celsius in pure water, hydronium and hydroxide ions concentrations must be equal, and they're both going to be equal to this 1 times 10 to the minus 7 molar. And so using the equations 1 and 2 for the pH and pOH, minus log of H plus and minus log of OH minus respectively, we plug in the values for this pure water solution, we get minus log of 10 to the minus 7 in both cases, and we find that the pH and pOH for pure water are both 7, right? And we define this as a neutral solution. All right. Also, at 75 degrees Celsius, this gives us some quantitative criteria for basically measuring when we're going to have an acidic or basic solution. Anytime your hydroxide or hydronium ion H plus concentration goes above 1 times 10 to the minus 7, and also there'd be a concomitant decrease in OH minus below the 1 times 10 to the minus 7 concentration values. Anytime that occurs, you're going to have an acidic solution. Similarly, you'll have a basic solution if hydronium ion concentration falls and hydroxide ion concentration increases. Okay, so now we're ready, I believe, to look at an example problem involving a pH calculation. So in this example, we're asked to determine what the pH of stomach acid will be, right? Which stomach acid is a solution of hydrochloric acid with a hydronium ion concentration of 1.2 times 10 to the minus 3 molar. All right, so the solution is pretty straightforward. We're going to use equation 1 directly. We have pH is minus log of our hydrogen ion concentration. We take minus log of 1.2 times 10 to the minus 3. We get our value negative 2.29, take the negative of that, and we get a pH of 2.29. All right, so fairly straightforward application of equation 1. Now we can ask pH and pOH questions in a slightly different way as well. In this next example, what we're going to do is calculate the hydronium ion concentration of blood given the pH value, which we're told is 7.3. In other words, it's slightly alkaline. And so from the problem, right, we know, we can set up our equation 1, pH is equal to minus log of the hydronium ion concentration, which we're told is 7.3. All right, so our task here now is to take our equation 1 and solve for that hydronium ion concentration. So to do that, we need to now remember that the logarithm we're dealing with in this pH scale is the base 10 logarithm. And so if we want to calculate, we want to solve and isolate the hydronium ion concentration, the hydronium ion concentration will be given by essentially taking both sides and raising them to the 10th power. So 10 raised to the log base 10 of hydronium ion comes back and simply returns just that hydronium ion concentration. Similarly, on the right-hand side, we take 10 raised to the minus 7.3 and plug that into the calculator, and you find a hydronium ion concentration on the order of 5 times 10 to the minus 8 molar, which again is less than the 1.0 times 10 to the minus 7 cutoff for defining a basic solution, right? And so we have this pH that's slightly above 7, corresponding to a slightly alkaline solution where our concentration of hydronium ion is greater than 1 times 10 to the minus 7 molar. Okay, so all of that hopefully is fairly straightforward, but there is one sort of sticky point here that is a point of confusion that I want to take some time to clear up regarding significant figures when working with logarithms. All right, so I'll keep it simple, kind of to the point here. When we're working with logarithms, the value after the decimal is what represents the significant figures. All right, so we're going to be really focusing in on, okay, what are the values to the right of the decimal place? Keep track of sig figs there. So if we're given an example where we're asked to find the pH of stomach acid, and this is the problem we worked through previously, we started off with this concentration of 1.2 times 10 to the minus 3 molar, which of course is 2 sig figs. We're using equation 1, right? And we plug it in and we arrived at this value, and we previously reported this value, 2.92. Now, at first glance, this might look like we have 3 sig figs, but remember, it's the value after the decimal point that is significant, okay? So in reality, the 2 sig figs here are represented by the 2 sig figs here after the decimal point, and this 2 on the left of the decimal point is in fact not significant. And so it's important to keep this point in mind when you're either calculating a pH or calculating a concentration from a pH. So another example, so we can follow through and make sure that we're understanding the sig fig concepts here. Let's look at what the pOH and pH are of a 0.0125 molar solution of potassium hydroxide. All right, so KOH, as hopefully you remember from previous chemistry studies, is highly soluble. It'll actually break apart completely, essentially complete dissociation to form OH minus. So if you start off with a 0.0125 molar solution of KOH, you'll end up with a 0.0125 molar solution of hydroxide ions. We can then plug that hydroxide ion concentration into equation 2, taking the minus log of this value. Minus log gives us a 1.903, where again, we have 3 sig figs reported here in the pH, corresponding to the 3 sig figs in that given initial concentration. Now, a little follow-up, the next part of this problem asks us to determine the pH. Well, there's a couple ways we can go about doing this, but remember, we have a very simple way using that relationship that we established earlier in the lecture that says, hey, look, if you're at 25 degrees Celsius, the sum of the pH and pOH is going to be equal to 14. So if you've already determined pOH, you can find pH by just taking 14 minus that pOH and reporting that value. Now, notice that we've effectively reduced our number of significant figures here. And so in cases like this, one of the goals is to always use measured values or reported values that are sufficiently precise so they don't limit your calculation. In practice, that's always a good idea to follow. And so in this case, you could also go through the opposite form, which is logically equivalent, but you could say, hey, look, I know what OH minus is, so I could use my KW expression to solve for H plus concentrations and then take minus log of that H plus. But remember, that is effectively what we did when we built up this relationship. All right, and so now we're in a position to round out this lecture by simply highlighting a couple common pathways that we follow for measuring pH values in a laboratory setting. So one of the standard approaches that you'll see in most laboratories are something that we call, a pH meter. And so this effectively is it's a device that uses electrical conductivity and related concepts to essentially measure, come up with a digital reading of what the pH is for a given solution. All right. Now, if you don't have access to, research grade digital instrumentation, another common approach is to use color indicators. So for those of you that have perhaps, taken care of a pool or done, basic chemistry laboratory experiments, you likely have some experience with, essentially using different indicator substances, paper, litmus paper type tests, and color comparison tests to come up with a rough idea of what the pH is for a given solution on the basis of color changes. Right. So of course, these have the benefit of being relatively cheap, easy to apply, but they of course don't have the resolution that digital pH meters have that are research grade. All right, so now that we've got the concepts of pH and pOH down, what we're going to start looking at now is how we can use more concepts from our chemical equilibrium discussion to compare the relative strength and weaknesses of different acids and bases. And we'll jump into that in our next video.